Hello MIT Lab team, we are Axel, Ivan and Daira, and today we'll be briefly presenting the results of our data science project for the Nanostore operation dataset. Our presentation is divided into three parts: project planning, database preparation, and model generation.
To begin the project, we work on understanding the main problem affecting a nanostore performance, which was using a pre-problem, which is page 2 of our document. We identified that the central issue is the lack of information about the factors that influence of the nanostore operations. This leads to the consequences such as inefficient processes and low business performance. Then on the objective tree, on the page number 3, we transformed the problem into a clear goal: generate reliable uh, statistical models that help us to understand and improve this performance of the nanostores. After that, we created a SMART objective, defining the scope of the project and what we wanted to achieve within the course timeline. We also developed the work breakdown structure, or WBS, and the WBS dictionary, which are on the page 4 to 7. And this helped us to divide the entire project into manageable activities, assign responsibilities, and understand dependencies across the task. Next, we built a Gantt chart and project network organizing the sequences of activities throughout the weekend. And finally, we perform a risk analysis identifying the potential issues such as the delays from the supporters, incomplete interviews, or the data collection mistakes. These planning tools ensured that we had a structured approach before starting the data analysis.
For the second stage, we focused on preparing the database to make sure the information was clean, structured, and ready for statistical modeling. First, we reviewed all columns, classified them as numeric or categorical, and removed the irrelevant fields, such as identifiers, geolocation, and metadata that didn't contribute to the analysis. Next, we corrected corrupted symbols to guarantee the consistency in the text fields. Then, we handled missing data using mode imputation, which is appropriate for categorical and discrete values. This allowed us to keep as many rows as possible. We also converted all categorical variables into numerical codes, since regression models require numerical inputs. With a clean dataset, we developed several graphs and explanatory analysis. These visualizations helps us better to understand behaviors in the data. For example, basing on Instagram's, most stores rely heavily on delivery services. It was observed some patterns in attitudes such as friendly, rude, or transactional behaviors, and the distribution of the Q1 variable was clearly multimodal, meaning the population has several distinct behavior groups. These insights help us to confirm that the clean dataset was coherent, representative, and ready for modeling.
In the final stage, we generated 3 types of models, which were a simple regression, a multiple regression, and a logistic regression. These always using techniques aligned with the introductory level of this course. For the simple linear regression, we modeled the target variable Q12 using only Q422, which were the variable with the highest correlation. The model achieved an R-square of 0.48. This meaning it explains about 48% of the variability. Although the residuals were not normally distributed, the model serves as a solid baseline. For the multiple regression model, we created 2 improved models. We have the model A, which used 3 predictors, which were Q422, Q432, and Q11. These 3 had an adjusted R-square of 0.42. For the model B, we used 2 predictors, which were Q422 and Q432. These had an adjusted score of approximately 0.48. The 2 models both improved slightly over the simple model. Model A performed best, but Model B is simpler and it is still strong. And finally, for the logistic regression, we converted the target into a binary variable based on a median. This regression, the logistic regression, reached about 86% of accuracy and a AUC of 0.88. This showing excellent discrimination between high and low performing shops. And now for some action scenarios, we propose three decision-making scenarios based on our models. For the first scenario, we improve performance by focusing on Q422, since this variable has the strongest positive effect. Improving it can directly raise Q12. Then for the scenario 2, we prioritize the stores using the multiple regression model. The stores with high negative predictors like Q422 and Q11 can be targeted for corrective actions. And for scenario 3, we classify store risk using the logistic regression. Here the stores can be labeled as high risk, medium, and high performance. This lets managers allocate resources efficiently. With these models and scenarios, we demonstrate how basic data tools can be support decision making in the Nanostore ecosystem.